Hi, welcome you all. I think you have checked my video on NTM of module 3 in my earlier video, which is as per the syllabus of VTU 18 scheme. Now in this video I am going to discuss on module 4, which is on electric discharge machining as per the VTU syllabus 18 scheme. Further, again I will be continuing. If you have any doubts, please mail me back with the contact details which are present with this video. Let me go with the EDM. Next is about the material removal rate. In my last video I discussed about the electrode wear, mechanism of material removal, dielectric medium or fluid characteristics or desired characteristics or essential properties of the dielectric fluid, or even the type methods of flushing, feed control mechanism, spark generators. All those things are discussed in my last video. Now I am moving to the next topic, that is the material removal rate. These all generally we consider it under a process capabilities or process characteristics. In EDM, the metal is removed from both workpiece and the tool electrode. The metal removal rate mainly depends on the workpiece material, but on the material of the tool electrode and the machining variables such as pulse conditions, electrode polarity and the machining medium. In this regard, a material of low melting point has a high metal removal rate and hence a higher surface, rougher surface. Typically, metal removal rates ranges from 0.1 to 400 millimeter cube per minute. The material removal rate or volumetric material removal rate in millimeter cube was described in by Kalpak Jain. It is given as VRR or volumetric removal rate is equal to 4 into 10 raised to 4 I into TW raised to minus 1.23, where I is the EDM current and TW is the melting point of the workpiece material. Here mainly material is removed in the form of a sparks, mainly removed by the sparks, and it is removed in the by forming a craters on the workpiece surface. The larger the craters are being formed, the larger the material removal rate. So here and further, it is, as I mentioned, it is mainly removed by the help of electric discharges of the spark. The spark is nothing but it is a source of electrical energy, and this electrical energy is mainly dependent on the current which is applied in the electric circuit. And the second one is the melting point of the workpiece material. Mainly the material is being removed in the form of by melting the by melting the surface of the workpiece, and it is being vaporized. The melting of the workpiece material itself is the primary stage here. As low as the melting point, the material removal rate will be higher. Here we can see there is a inverse relationship which exists between the material removal rate and the melting point. The higher the temperature of the lower the temperature of the melting point, the higher will be the material removal rate. Higher the melting point, the more amount of energy is required for melting of the molten metal from the surface of the workpiece, and obviously it reduces the volumetric material removal rate from the workpiece. The inverse relationship which can be deduced from this equation, which is saying that volumetric VRR is material removal rate, volumetric removal rate, which is equal to 4 into 10 raised to 4 I into TW of minus 1.23. The pulse frequency is like for 5 kc current which is required in the range of 1 to 20 amps. Generally the surface roughness which is obtained is in the range of 6 to 12 microns, whereas the crater depth is in the range of 0.05 to zero point 0.1 mm, where the crater depth which is formed on the electrode is in the range of 0.03, whereas the material removal rate which can be achieved with respect to the workpiece I am speaking, it is in the range of 460 millimeter cube per minute. Similarly, as I am increasing the pulse frequency, even the current required goes on increasing. Like up to surface roughness is in the range of 1.2 to 2 microns. Yeah, for a higher pulse frequency with low current density, we can achieve a better surface finish. But again, it will lead to a lower material removal rate. We can see like at pulse frequency 10 and current amps in the range of 5 to 17 amps, current usage will result in 4 to 6 microns, which is a better surface finish. Also use a better material removal rate around 130, which is lesser than the desired. So higher the increasing the current will increases the uh, greater depth, sorry, decreases the surface roughness also, MRR. But so optimum selection of the current is also very important aspect here. Coming to the voltage effect on the material removal rate, with the increase in the mean current, we can see here the material removal rate goes on increasing continuously up to 14 millimeter cube per minute, with the increase in the current amps up to the range of 4 amps. On the other side, the plot has been made for two different voltages, around 200 volts and 150 volts, which we can see here. For the dielectric fluid, kerosene and a tool which is brass, and workpiece material is low carbon steels. For a tool electrode area of same tool electrode area which is around the range of 78.5 millimeter square. When we see the two lines which is plotted for two different voltages, 150 volt and 200 volts, we can see that the increase in the voltage will directly affect on the metal removal rate, and it increases rapidly the metal removal rate for shifting the line from small 150 volt to 250 volt. The drift of the shift of this voltage will increase, or the increasing the voltage will rapidly increases the material removal rate, because mainly we can say that it is the discharge energy which is available at the tool work gap or the machining zone is very high enough for the metal removal from the workpiece surface. This is a major important characteristic or parameter which need to be considered to achieve a better metal removal rate. But obviously when we say about the metal removal rate, we also need to make a compromise at the surface roughness, because when we say a higher material removal rate, it is mainly desired during the roughing operations. When we go for a finishing operations, rather than we concentrate on the material removal rate, we mainly concentrate on the surface roughness which is being formed on the machine surface. uh, so in that case, generally we go for, when the surface roughness is being concentrated, the material removal rate or MRR or VRR will drop down, because the small craters are being formed in a unit period of time compared to the size of the craters, or the material which is being replaced from the surface of the workpiece also will drop down. That's why the MRR and surface roughness, a compromise has to be made, so that a better quality machine surfaces are being obtained with a decided tolerances and dimensional accuracy on the workpiece. On the other side, let me go compare on the machining area also. Here when we are increasing the machining area on the tool, the increasing the machining area from 0 to 380 300 to 380, nearly up to 310 320 millimeter square, the machining area is increased on the tool. The increasing the cross sectional area of the tool will increases the material removal rate up to some threshold value or to some peak value, after which thereby decreases the material removal rate. The material removal rate will fall down after further increase in the material removal machining area on the workpiece surface, or a cross sectional area on the workpiece surface. The major reason which is being called here, which is causing the material removal rate to be fall down after the threshold value, it may be one possible reason is like when the material removal rate machining area is increasing, the energy which is present between the tool and the workpiece also get distributed over the surface of the machining area, and because of which the energy required for the removal of material over the workpiece also get decreases, because of which the material removal rate decreases. That is one of the possible reasons because of which the MRR will fall down after some threshold value. Till then, the material increasing the material removal rate, which increases the larger area for the interaction of the tool and the workpiece, which can absorb more amount of energy or distribution of more amount of energy over the surface area of the workpiece, which increases the material removal rate. Further, in this plot, we can observe we can see that the increase of material removal rate across for pulse energy. When the pulse energy is increased, even the material removal rate goes on increasing. Nothing but with the increase in the material removal rate, with the increase in the pulse energy results in, so increase in the pulse energy will increase the energy available for the removal of material from the workpiece surface. It is nothing but the energy which is available for the replacement of material from the surface of the workpiece, or melting of the material for amount of energy which can be available for the transferring of kinetic energy into a thermal energy. So when the same amount, when nearly same amount of kinetic energy is being transferred to heat energy, the higher amount of energy, thermal energy, is being generated, which is going to cause the larger volume of material to get melted completely and it get replaced from the workpiece surface. So by that way, the pulse energy will increases the amount of energy which is available for the material removal. So material removal rate also goes on increasing with the increase in the pulse energy. Further, again we can see here, with the increase in pulse energy, with the increase in voltage voltage value also further increases the material removal rate to a very greater value. It is the most important process characteristic which we need to understand. For roughing operation, we have to use a higher pulse energy or discharge energy for the achieving a better material removal rate or higher material removal rate. Coming to the relative voltage at a discharge compared to relative capacitance. It is less studied at the UG level, but still let me give a small introduction about this process characteristic. Here, with the increase in the relative voltage after discharge, even the relative capacitance goes on increasing up to a certain level of up to say around 60 to 70 relative voltage at discharge. The relative capacitance goes on increasing, but further increasing in the relative voltage at discharge will reduce or will diminishes the relative capacitance value. uh, Further, to achieve to determine the suitability of material for applications as electrode tool material in medium, there are the important factors are being like a higher material removal rate is one important major factor. Further, like the lower tool wear and high degree of electrical efficiency are also being considered as other factors which determines the suitability of material for application as a electrode material for EDM. Material removal rate, though it even we consider it as a process characteristics, even that is also one of the important parameter or a factor which is used to determine the suitability of a material as a electrode material. Generally, like a good conductor materials can serve as electrode. The factors and properties essential for better application in EDM graphites, as we had discussed in earlier slides, it is a better suitable tool material. Further, it reduces the low wear rate as with a high degree of electrical efficiency, and they are easy to fabricate because of its easily machinable characteristics and of lower cost. But a good isotopic grain structured graphite with fine grains possessing same current carrying and wear characteristics in any direction make excellent tool material for EDM. Copper, tungsten are also extensively used as tool material. Further, minimum tool wear conditions can be obtained in EDM using graphite electrodes with frequency of around 3000 kilohertz at 30 amps power supply. A coating of steel on a graphite electrode is given to control the actual wear of the graphite, but no wear machining condition produces a workpiece machine surface very much rough for most machining applications. Produces most machining condition produces a workpiece machine surface very much rough for most applications, and a finishing cut is invariably needed. Different electrode materials used in EDM and their characteristics, we can see like graphite with high material removal rate with low wear ratio, fabrication is easy and cost is higher. Whereas when we go for a steel, it is the material removal rate is very low, whereas the wear ratio is very high and fabrication is easy, and at the same time the cost is very low compared to graphite. As the major operating factors of a material removal rate, the wear ratio and machining stability are dependent on power supplied to the system, and selection of tool material, tool electrode material is governed not only on the workpiece material to be cut but also on the type of machine used. Further, the amount of clearance to be provided depending on the material removal rate, tool material and material of the work to be machined. It also depends on the nature of the cut, like roughing and finishing operations. In machining hardened steels with brass as tool material, the side clearance to be provided is 0.25 mm. The duraluminum, the clearance will be 0.3, and graphite electrode it will be 0.35. With higher material removal rate, the clearance to be provided is also around 0.5 mm. For medium rate, it will be around 0.3 mm, and slow rate of cutting or fine surface, the clearance will be of 0.05 mm. These are the some of the aspects which are related to the metal removal rate or a process characteristic of MR or volumetric removal rate. Also, we can call in simple as a volumetric material removal rate. Further, it is like MR is basically, as we have discussed in the other slides also, it is basically a function of current and the melting point of the workpiece material. The material removal rate mainly depends on, like, we can summarize it like MRR mainly depends on following factors, like one is peak value, peak current or intensity of the spark, length of the on time, the spark on time, voltage across the gap. Duty cycle are nothing but the percentage of on time relative to total cycle time, and the gap distance, that is slower, is the material removal rate, as the pulse of time, which decreases the MRR but reduces the heat affected zone and improves the accuracy. These are some of the this is the summary of material removal rate. In simple, MRR is closely connected with the pulse characteristics as well as tool electrode and also workpiece thermal characteristics and dielectric properties, dielectric fluid properties. Like in a tool electrode, if I am going for a sub case, the tool electrode material, the tool electrode movement and tool electrode wear also directly affect on the material removal rate quality. Similarly, for the workpiece material characteristics, melting point, boiling point, conductivity of the workpiece material also directly influence on the material removal rate, surface quality as well as the accuracy too. So this is the summary of the effect of MRR, and at the same time we can also say that increasing the factors will increase the MRR, but at the same time at the cost of surface roughness and the accuracy. So we have to take a proper decision to increase the MRR based on the desired application. So in the next video, I will be discussing on the surface quality, surface integrity characteristics of the workpiece machined with the EDM. So thank you. Hi, you have watched this video. Yeah, I hope you understand regarding this EDM. To the topic which I had discussed in this video. Thanks for watching and a patient listening to this video. I thank to all my colleagues, management and principal for encouraging me to make this video. I also declare here as a disclaimer that I have used many resources, textbooks and other reference materials and internet sources for preparing this video as a teaching material. And I acknowledge all such sources um, through this platform, and I also thank all such sources which has helped me to prepare this teaching material. So thank you all regarding this. Thank you. Watch my next video.